Today's lesson is a big one. It's called the limit definition of a derivative function. Let's recap. So far, we know how to find the slope of a tangent line at a specific value. We also call that slope the instantaneous rate of change, or the derivative at a point. And we can do that if we're given a function written out as an expression or an equation. And we can also sketch the derivative function based on visual cues. If we see the graph of a function, we can look for the turning points, the horizontal asymptote, not asymptotes, the horizontal tangents, the points when the function is increasing and decreasing, and we can make a sketch of the derivative function. But we want to do better than that. What if we want an exact derivative function, an expression in terms of x that we could evaluate at any x value we want? So that if I gave you a function, let's say e to the x minus 3x squared plus the cosine of the ln of x. That's a crazy looking function. What if I wanted to know a derivative function that if all you had to do was tell me an x value and I could plug it into some expression and find the instantaneous rate of change of this crazy weird function at any value for x? Well, that's what we're going to do now. So let's take a look at a graph of a function. This function is f of x. Should label it that way. The point that's marked with a question mark right now, that's the x value that's where we want to find the instantaneous rate of change, which is not the slope of that blue line. We'll get to that in a second. Well, I want to find the instantaneous rate of change of this red f of x at that value right there. But here's the problem. I can't call it c because I don't want it to be stuck in one place. I don't want it to be a fixed constant. I want that question mark to be variable. I want to be able to find the instantaneous rate of change no matter where that question mark is. Well, so we can't call it c, we've got to call it x. But in order to talk about rates of change, same thing we did last week, we have to talk about another point on the function. So I need another name for that other point on the function. The only problem is I can't call it c or a or b because it can't be stuck in one place. And I can't call it x because I've already got a name there. So this brilliant little stroke of genius is to, instead of focusing on what this other point is, because remember what we've done several times in the last week when we talked about the derivative at a point, was we don't want to be stuck with the slope of this blue secant line. We want to eventually make that secant line get closer and closer and closer to the tangent line that I haven't even drawn yet, which means we're going to want this point to move. So this is going to be something that moves, and we're going to take the limit as it moves over, but I can't call it x. So instead, what we do is we say, all right, let's focus on the distance between x and that point, that distance. And we call that distance h, for reasons I couldn't even begin to explain. I have no idea. But we call that h, which means that that question mark right now, the spot that I'm working on labeling, would be whatever x is plus whatever that distance is, x plus h. And so that's what we will call the other point on the x value, on the x-axis. And what's great about this is we're using that same variable x for both of those 2 points, and that's going to be helpful for us later. The next couple of steps should be easy. That y value, of course, I'll call it, because it is the y value on the function when the input is x, that means the output would be f of x. And then the output later on, when the input is x plus h, would of course be f of x plus h. And now we can focus on the lines themselves, the slopes that we want to calculate. Because the coordinates, and I'll just put them here even though we have them labeled pretty well on the x and y axis, I'll put them here anyway. The two coordinates on this blue secant line are x f of x and x plus h f of x plus h. And as we know from last week, the goal is to find the average rate of change and then imagine it getting closer and closer and closer to the instantaneous rate of change by moving that secant line until it basically looks the same thing as that green dotted tangent line. Well, in order to do that, we need to think about what the formula for the average rate of change would be. And remember, the other name for the average rate of change is difference quotient. And so the formula for the difference quotient would be the difference in the y values, which would be the higher y value minus the lower y value. And I shouldn't say it that way. It doesn't have to be the highest minus the lowest. It's just in this case, it's the highest minus the lowest, which would give me that distance divided by the difference in the x values, which I certainly could write as x plus h minus x. But remember, the point was we already gave this distance a name. We called it h. So I'm just going to put that h down there, which of course is the same thing as x plus h minus minus x. That would give me h anyway. So that's what goes in my denominator. And so just like we saw last week when we were looking for the derivative at a specific point, this week, when we're talking about the derivative at whatever x happens to be, I'm still going to think about moving that blue secant line over, taking this x plus h, dragging it over this way, so that this blue secant line becomes closer. So I should be doing that in blue. Becomes closer and closer and closer to being just like that green dotted tangent line. So that way the rate of change of the average rate of change, the slope of the blue secant line, will be the same thing as the instantaneous rate of change, the slope of the green tangent line. All I need is the derivative. So the instantaneous rate of change, or the derivative, which we're going to call f prime of whatever that spot on the x-axis we want to find f prime of, or f prime of x. Notice that that's function notation. This is setting it up so that way we can plug in whatever number we want for x. Would be the limit of my difference quotient. I'm just copying what I've already written down over h. As this point moves closer this way, which means this distance, that h, is getting smaller and smaller and smaller until it becomes nothing. So we're going to take the limit of the difference quotient as the distance between the two x values approaches 0. And this is a big deal. This is what we call the limit definition of a derivative. And I do apologize that this one's called the limit definition, even though the other definition of derivative at a point also had a limit in it. I'm sorry, I did not make up the names. And an important note, by the way, in some places you'll see that h given the name delta x instead of h. I think that's silly to use a symbol like that when you're only talking about one thing, but other people use it, and so just don't get thrown off if you see a delta x in there. That would be in the spot of this h, and this h. It doesn't change anything, it's just a different name for the same thing. So let's take a look at an example here. We'll actually do two examples and see them both in action. So if f of x is x squared minus 3x plus 2, and we want f prime of x, the derivative function for f, or the function rule that we could plug x into to find the rate of change at any point we wanted, it would have to be the limit of the difference quotient, which is f of x plus h, which is a little bit tricky to write. F of x plus h, remember that's this piece what I'm looking at right here, that would require taking x plus h and plugging it in to both of those x's. Well, that's going to be a little bit messy. X plus h squared minus 3x plus h plus 2 minus f of x, which we already have f of x, so I can just write it down, Yep, I just did that. Notice how I'm changing the signs here because it's minus f of x. Since f of x is this quadratic, I'm distributing that minus sign as I go. Please be careful about that. Over h as h approaches 0. And this requires a lot of cleaning up. By the way, you should probably guess that if I were to try to evaluate this limit by direct substitution, just plugging in h as 0, I would get 0 over 0. So that means we're going to have to clean it up a little bit. So let's work on that numerator. I'm going to have to FOIL out the x plus h squared, distribute the negative 3x plus h, and then see where we are. So I'm going to FOIL out the x plus h squared. X squared plus 2xh plus h squared minus 3x minus 3h plus 2 minus x squared plus 3x minus 2. That's a lot over h. I know that's a lot. Don't worry. In a couple of classes, we'll do, well, much more. But I do want you to notice that a bunch of these things cancel. The x squared and negative x squared cancel out. The negative 3x and plus 3x cancel out. The plus 2 and the minus 2 cancel out. So if I rewrite it with all of those terms just completely ignored, it's 2xh plus h squared minus 3h over h as h approaches 0. And we still have the same problem that we haven't fixed yet, which is if we do direct substitution, we get 0 over 0. But at least now it's set up so that if I factor out the h, it'll cancel. And once those h's cancel out, direct substitution would be no problem. I can plug in the 0 for h right there, and I'm left with 2x minus 3. So f prime of x is 2x minus 3. Which, by the way, just doing a quick check to make sure that sort of matches up with some of the things we've said before. Notice how f of x was quadratic and f prime of x is linear. Just like when we were doing our graphs, we saw that the parabolas, when the function was a parabola, its derivative was linear. So that does work. I'm going to do the next one also, just to give you another example. G prime of x is equal to g of x, the limit of the difference quotient, so that's g of x plus h. Ooh, that looks like it's going to be annoying. Minus g of x over h as h, not x, as h approaches 0. Which again, just the understanding the foundation behind this makes it much easier to remember. All that I'm doing here, and I know it looks messy, but all that I'm doing is saying this is the difference quotient, the difference between up here and down here, rise over run. And I'm going to take the limit, because remember the run, that's what we call our h, and I'm going to take the limit of that difference quotient as it gets closer and closer and closer to being a tangent line. If you can kind of explain that logic in your own words, you're in very good shape. Just undo that, get rid of the highlighting. And sure, this one's a little bit messier, but the truth is it's not too bad. I'm going to work on that numerator. I'm just going to work on making a common denominator there. So I'm going to need to multiply the first fraction up in the numerator by x over x, and the second one by x plus h squared over x plus h squared. I'm sorry, that should be x squared. all of that is over h. And remember, we're taking the limit of this whole big thing as h approaches 0. It is a little bit silly to write it this way. When I said the whole thing over h, I'm just going to point out, and this is something for you to get used to just in general, when you have a fraction already in a numerator, and then your denominator is something super simple, just like a simple h, just stick it, instead of making a whole nother big denominator, just stick it into the denominator that's already there. And that accomplishes the same thing. I am going to have to do a little bit of simplifying in the numerator again. I'm going to have to FOIL out that x plus h squared again, and I'm going to distribute the negative. You should try that on your own and make sure that you get the same thing with all the correct signs when I'm done. There is absolutely no reason to FOIL out the denominator. There is almost never sorry, put that square in the wrong spot. There's almost never a reason to FOIL out a denominator. Leave denominators factor. And so again, there's a little bit of canceling to help us out in the numerator. And what's left, we have an h to factor out. So I'll cancel out those x squareds, and I will factor out an h. Again, you should be doing this on your own, making sure that what you're getting is the same as what I'm putting up here. And the h's cancel. And when we do the direct substitution, because remember, the h's cancel out, leaving me still with a limit of negative 2x minus h over x squared times x plus h squared. And what that leaves me with is do the direct substitution. Negative 2x minus h becomes negative 2x minus 0. And the x squared and x plus h squared, well, x plus h is just x. So that's x squared, or x to the fourth. And of course, we can cancel out one of those x's. We get negative 2 over x cubed. That is g prime of x. And so those are a couple of examples of using the limit definition of a derivative function to find the derivative.